In this video, what we're going to do is to develop a more general equation to describe our second order systems. The reason we want to do that is so that it's easier to describe the response type. So as we saw previously, we had described our second order systems with g of s equal to b divided by s squared plus as plus b. And so we could find the poles of the denominator, the poles of the system, and we could determine the response type. But we want new variables such that we can just look at those variables and say right away what type of response we have. So it turns out we're going to define two new variables, the first of which is our natural frequency. And so we're going to use the variable omega sub n to indicate our natural frequency. As the name suggests, this is going to be the frequency of oscillation for our system when we have no damping. So frequency of oscillation of our system without damping. The second variable that we're going to define is our damping ratio. And so for our damping ratio, we're going to use a Greek lowercase letter zeta. And so what our damping ratio is we want to indicate the level of damping with respect to the period as opposed to elapsed time. So indicate our damping with respect to period of our signal. And that's as opposed to elapsed time, which is what we were doing previously. So we can say that our damping ratio is equal to our exponential decay frequency divided by our natural frequency. And so this natural frequency is typically going to be in radians per second. We could also express this as 1 over 2 pi, so that's going to convert this natural frequency in radians per second to a natural period in seconds. So natural period in seconds, and then in the denominator, we know that our exponential decay frequency is the inverse of our exponential time constant. So exponential time constant. So either of those representations for our zeta are fine. So what we want to do now is we want to relate these two new parameters, our omega n and our zeta, to our b and our a that we had in our previous representation. In order to do that, we're going to consider a couple cases. So let's start by considering this natural frequency. So it's a frequency of oscillation of the system without damping. So of course what we should consider is our undamped response. So let's consider our undamped response type. And we know that this occurs when we have two imaginary poles. So remember they were on that j omega axis. And so what that means is that our a is 0, so i.e. a is equal to 0. So what we ended up having was g of s is equal to b over s squared plus b. So we had something that looks like this. So the frequency of the response, we saw frequency of response in a previous video. We said that that was equal to square root of b. And so essentially that's just by finding the pole, or the two poles of that denominator, or the poles of the system rather. So by definition then, our natural frequency is a frequency without damping. Our undamped response is a response with no damping. So we can say by definition our omega n is equal to square root of b. So this value here. Of course we can write that as b is equal to omega sub n squared. So now we know how to relate b to our new parameters. The next thing we want to get is a relationship between zeta and our old parameters a and b. In order to do that, because we already have this information for our omega n, we can consider another response type. So let's consider our underdamped response type. And for our underdamped response type, we're going to be looking for that relationship to a. So what we had seen in a previous video is that for our underdamped response, we have complex poles, and the real part of those complex poles, and so I didn't point this out explicitly, but if you go back to the notes on Canvas, or if you go go watch the previous video, the real part of those complex poles is alpha is equal to negative a over 2. And so that's of course where our a is coming from this general equation we had previously. Okay, so knowing that, we can then say that the magnitude of our sigma is our exponential decay frequency. And that's based on the natural response form for our underdamped case. So exponential decay frequency, magnitude of sigma. So based on our definition of our damping ratio zeta, we have that is equal to the magnitude of sigma divided by omega n, our natural frequency. So subbing in for our magnitude of sigma, we know that's a over 2, so we've lost the negative sign because we took the magnitude, and we still have divided by omega n. And so putting all of that together, we have that a is equal to 2 omega n times zeta, or alternatively, we could say that zeta is equal to a divided by 2 times the square root of b. So now we can relate our a and b to our omega sub n and our zeta. So we can rewrite our general expression. So we can now write g of s is equal to, and in our numerator we're just going to have our natural frequency squared. In the denominator we have s squared plus 2 times zeta times omega n s plus omega n squared. So we get something that looks like this. Now, it's worth noting that this equation, as well as the general one we stated before, are for the case of unity gain. And so what does unity gain mean? Well, it just means that our gain is equal to 1. As I said before, we could of course multiply this by some constant, so we could come in here and multiply this by some constant value k. If we wanted to have a gain for our system, same thing with our general equation in the previous form, we could multiply by some constant k here, where k is our gain in both of these cases. So let me write that explicitly here. This would be k is some gain. But without the k shown there, we have this unity gain system.